Hi guys, Miss O'Connell here. So today is Friday, December 10th. We're going to be talking about how to determine the initial velocity of a projectile when that velocity is unknown and we are given the range and the height of that object. So materials that you need out right now are your pencil, calculator, note card, and your non-horizontal launch guided notes from last class. So those notes that we took last class, we're going to need to pause the video and take that out. Okay, so we're going to start with that do now on the non-horizontal launch guided notes. Just some reminders, you do have your test not next period, but the following period. Homeworks for this unit so far have been the vector practice worksheet, the free fall textbook problems, the 8 projectile motion problems from last class, and then the Unit 3 test review. Okay, so non-horizontal launch notes, that front page is going to look like this. So you have non-horizontal launch. We did the problem with Jay and Zach. On the back of that page, you'll see your do now and the non-horizontal launch example. So you're going to take a minute, pause the video, and try the do now on your own. Unpause the video when you're ready for example 2. Okay, so this example is going to give us the procedure for our next lab. So this example is pretty important. You're going to want to make sure that you have this copied down on your guided notes, which I will be checking when I return to school. So for this problem, we have Andrew. He hits a golf ball 110 meters down the golf course to sink a hole in 1. Okay, so you have that path of motion that's drawn out on your guided notes. We're going to add a little bit to this diagram here. So Andrew sinks a hole in 1. So that means that the path of the golf ball, the ball leaves the tee and lands directly in the hole. From the initial location to the final landing location of the ball, which is right here, that change in horizontal displacement, that range is 110 meters. The golf ball lands in this position, hits that hole in 1 7 seconds later. So it takes 7 seconds to get to this position here. The initial height of the golf ball is on the ground. The ball lands 3 meters above that initial location. So here's why initial. Initial location is 0. Compared to our initial location, the ball is going to land 3 meters above the origin. So that means that the change in the height, from initial height to final height, delta y, is going to be 3 meters. So the final position is above the initial position. So delta y is going to be a positive 3 meters. We're asked to figure out how fast Andrew hit the ball. So how fast? What does that mean? It's asking for the speed or velocity of the object. Okay, so usually we're given velocity. We're given the initial velocity of the object, but in this case, we're not given that initial velocity. We have to figure out what that is. V initial is equal to question mark. In order to do that, we have to find both the x component and the y component. So I need to find the y component of this initial velocity. and the x component of the initial velocity in order to find the magnitude. Okay, lucky for us, the process to solve these is exactly the same. So our first step when we approach these, we're going to write out our givens, what we know, in both the x and the y directions. So what do we know? We know the height in the y, we know the range in the x. So let's add those to our t-chart. What else do we know? Well, we have time in both dimensions, right? Time is the same no matter which dimension we're moving in. So we have a variable for both the x and the y. We know time will be the same in both the x and the y. It's going to be 7 seconds. We don't know the initial velocity in the x or the y, but we do know that the acceleration in the x direction is always 0 for projectile motion because there's no forces acting on the object in the horizontal direction, only in the vertical direction. So we know that acceleration in the y direction is going to be negative 9.8 meters per second squared, because we said that down is negative. We're looking for initial velocity in the x, that's equal to question mark. And we're looking for initial velocity in the y, that's equal to question mark. So that's our first step. Write down what we know, what we're given, and what we're trying to find. Our second step is usually to find time using what we know in the y direction. We can head right to step 2, except instead of finding time, we're going to use that same equation to find the initial velocity in the y direction. So we're going to use the same process, but just to find a different variable here. So our equation, we're going to use delta y total, the total change in height, is equal to the initial velocity in the y times the time plus 1/2 times acceleration in the y times t squared. And we're going to plug in what we know. This time, however, delta y total is not 0, it's 3. So this whole thing is going to be equal to 3 meters. Initial velocity in the y direction, we don't know what that is. That's what we're looking for. So we're going to leave that as a variable. We know that time is 7 seconds, so we can plug right in for that. And acceleration is negative 9.8 meters per second squared. Time again is 7. Don't forget to square the time. When we square the time, we get 49 seconds squared. 49 times 9.8 times 1/2, we get 240.1. Our units, when we square the 7, we also square seconds. So we have meters per second squared times seconds squared. The seconds squared cancel out, and we're left with just meters. Okay, so because these have the same units, we can add 240.1 to both sides of the equation. On the left-hand side, we'll get 243.1 meters is equal to, rest of my equation is going to stay the same on the right-hand side. The 240 obviously will cancel out, but we have initial velocity in the y times 7 seconds. These are connected by multiplication. So to get initial velocity by itself, we divide both sides of the equation by 7 seconds. We got that initial velocity in the y is equal to 34.7 meters per second. So we found the y component to our velocity. The y component is 34.7 meters per second. Okay, so we found the y component. We still need the x component of that initial velocity. So we're going to head right to step 3. We're going to use a range equation, but this time, instead of finding range, we're going to use that equation to find the x component of the initial velocity. Okay, so that full equation, we have delta x equals initial velocity in the x times t plus 1/2 times acceleration in the x times t squared. So we know that acceleration in the x is equal to 0, so this whole segment of the equation will cancel out. We're told that delta x is 110, so for delta x, we're going to plug in 110 meters. We don't know the initial velocity in the x direction, so we're going to leave that as a variable. And time we have is 7 seconds. So we divide both sides of the equation by 7 seconds to get initial velocity by itself. And we find that the initial velocity in the x direction is 15.7 meters per second. Okay, so we have the x and the y components of our initial velocity. We are unfortunately not done because we need the magnitude of that velocity. So I have this kind of drawn over here, but I'm going to redraw it just to help us visualize a little bit. So we know that this is a vector, right? Vectors have magnitude and direction. Our x component is positive 15.7. I'm going to actually use red to represent that here. So we start at the origin, and our vector would be in the positive x direction, which means east, or along the positive x-axis. This vector component has a length of 15.7 meters per second. We add our vectors tail to tip. We calculated our y component to be 34.7. So my y component is going to be almost double. Length is 34.7. So you have two components of our vector. We need the magnitude of that vector. So we need the hypotenuse here and the angle. So we need to find this initial velocity value, v initial. Okay, so if we have two sides of a right triangle and we're looking for the hypotenuse, we use Pythagorean theorem, right? And we have those shortcut equations that helped us find the hypotenuse, okay, using the x and the y coordinates. So here's the x component of that initial velocity, which we called r sub x. Or sorry, this guy down here is r sub x. And this guy up here is r sub y, the y component. We have these equations on our note card, right? To find the magnitude of the vector, magnitude, this guy here, we square the x component plus the square of the y component, take the square root of the whole thing. We're going to do the same thing here with velocity. So the initial velocity is going to be equal to the square of the x component, which we have 15.7, squared, plus 13.7 squared. Square root of that whole thing. To get the magnitude. When we plug that into our calculator, we will get 38.1 meters per second. That's the magnitude of our velocity. We are not done yet. We need to find the angle. So theta is measured in between our vector and the x-axis. So to find theta, we're going to use the inverse tangent. Tangent. So we're going to head to our opposite side, which is the y component, over the adjacent side, which is our x component. So r sub y over r sub x. So we're going to take the y velocity, which is 34.4. Sorry, 34.7. I keep saying 0.4. 34.7 over 15.7. We're going to take the inverse tangent. So we're going to use the second button, and then the word tan on our calculator. That's going to give us tangent to the -1, our inverse tan. Calculator needs to be in degree mode so that the theta value we get is degrees. And we get 65.5 degrees. You can either say this is north of east or above the horizontal. Also works. Okay, so our final answer is 38.1 meters per second, 65.5 degrees north of east. That is the velocity that the golf ball was thrown at. Please make sure you have this on your notes because I will be checking it as a classwork grade that we tried to do now and wrote down the example. Your goal for the rest of class is to make sure, number one, that all of the questions on the projectile motion homework are complete. Number two, you're going to complete the test review for Unit 3. If you, for some reason, lost that test review, there's a copy posted in Google Classroom. The answers to the problems for the test review are also in Classroom. So please check your answers. We'll talk about any questions that we had in our next class. After we review the test review in our next class, we'll do the baseball toss lab, and your test will be the following class period. So please use this time wisely, as I expect you to come in ready with questions in our next class period. Have a great weekend.